Okay, in chapter 3, we're going to start talking about equilibrium. And a particle is in equilibrium if, let's go with weight, if it's at rest, and originally it was at rest. Or if it is in constant motion. If originally in constant motion. This is just the Newton's first law. So if this condition exists, then the second law degenerates to sum of forces equals 0, because this equals mass times acceleration. And since we have a constant mass, that means our acceleration is equal to 0. Okay, so let's talk about something that we want to use a lot as a good tool to help us see what's going on, something called a free body diagram. Now, you'll probably include a free body diagram in every problem you work on from this point on in this class. Let's set something up here. So let us say I have a weight hanging, circular weight, hanging by two ropes connected at A and B. And I want to figure out the forces on this thing and draw it in a free body diagram. Well, I could draw this like this. I'll have force vector in this direction. I'll have a force vector in this direction. This guy maybe I'll call the tension B. This guy probably tension A. But I have something else I have to represent here. And that is another force, which is the weight of this thing. So these are all the forces acting on this body. So one way to do this is you can just start at a point and start tracking around and see when you get to forces that are acting on the body, add them to your free body diagram. Okay, let's look at 3 common supports that we're going to be encountering over and over again in the class. First off, let's look at a smooth contact. Let's say a particle or object is resting on a smooth surface. It will, perhaps this thing is being affected by gravity, so it has weight. Then so let me move the weight up here. Then the force exerts, or the surface exerts a force normal to the surface here on the particle, in line with that other force, the force of weight. So I could draw a free body diagram of this situation, like so. Kind of trivial in this case, but as situations get more and more complex, this will be a useful tool. So let's look at this situation where I have a point on an incline, and have a force on it of T. Actually, I'll leave this off, and I will put on a direction here. So this force is acting at crashed. Software crashed, and I restarted it. So this is acting at 45 degrees to the vertical. And I want to draw a free body diagram of what's going on in this situation. So start with this particle, then I will have this force here of T, which is heading off at 45 degrees. So then there is a normal force that's normal to the surface, pushing up on this particle like so, 90 degrees to the surface, and that's our normal. And continuing around, so I hit the normal force, but also if there's any weight, we'll have to represent that in our free body diagram also. So coming down, these are all going through that point, though it's drawn a little crooked. So I can leave in this reference line if I want in my free body diagram. And I can determine, if I know, say, what this angle is, I can determine then that the angle between these two is going to be 30 degrees. And you should practice that, transposing the angle from here over to your free body diagram, how it's going to interact on your free body diagram. So how did I figure out that was 30 degrees? Go ahead and try to figure it out while I draw some. Let me draw these in a different color. I draw some reference lines here. So if I'm extending my incline down to here, we know from our problem that this was 30 degrees. So if this is 30 degrees, I come out and I can create this triangle here. This is 90 degrees here, because it's 90 degrees over here, which means this must be 60 degrees. So if this is 60 degrees and this is 90 degrees now, the weight is always vertical. Problems like this must be 30 degrees. Okay, next let's talk about cables and pulleys. Weightless cables and pulleys. All pulleys and cables will be considered weightless unless they are given weights in the problem. Sometimes your pulleys are given weights, but the cables are pretty much never given weights in a problem. So let's say I have a pulley attached to the ceiling like so, and I've got cable coming off of it on this end, and perhaps it's coming off at some angle theta. Then I have the other end of the line, so it comes around. Oops, I shouldn't have done that. Comes around, essentially comes around, contacts this at some point, comes around, and I want to pull down vertically on this cable like this. So with cables can only carry a tensile load, and they'll transmit that tensile load around the pulley to the other side. So the tables can't hold compression. Cables and ropes, they can only hold tension. So if I'm going to draw a free body diagram of this, I will maybe just draw the circle. I don't need much more. And then let's use a different color. I've got that force. Draw it again. This force in this direction. And then, since we're considering the pulley weightless right now, the only other thing I have is this force in this direction. But this pulley's not in motion, so something has to be holding the pulley up. And that means our bearing is exerting a force on the pulley, and I really want this to go through the point in the center of the pulley, like so. And we'll just say, call this the force of the reaction. And there we go. We've got all the forces accounted for in our free body diagram. Now we can analyze our problem. We could put what the angle is here. Okay, our third topic here is going to be springs, and we're going to talk about only linear elastic springs. Those are springs with a constant spring coefficient. So we're talking about maybe something like this, where you would have a spring and a force. Maybe the force is a weight. Then we'll have some pertinent dimensions here. Usually there's a undeformed length, and then we will have this spring will be stretched some delta, and when it's stretched we'll consider it, I guess, positive. And then there's just a total length we could represent here as L. So L0 is our undeformed length. L is the total deformed length, or the total length. And delta is the change in length. Well, so delta equals L minus L0. We can represent that force as K times our delta, or K as our spring constant, our linear spring constant. So representing this in a free body diagram, we might draw something that looks like this, where this represents our spring. We have a force pulling down equal to K delta, and then we have the reaction force from up here. You don't have to draw this line here, but sometimes it helps.